This program is brought to you by Stanford University.
When Mike was a kid, he was about 3 years old, he was playing in his parents' garage, and there were unfortunately some chemicals there that fell together and ended up causing a bit of an explosion. It was a very sad event. One eye that he had was completely destroyed. The retina, the eyeball, everything was completely destroyed. The other eye was very seriously damaged, particularly the front of the eye, the cornea and the sheet that covers the cornea was particularly damaged. And Mike lived that way with a very damaged eye of this sort for 43 years. Now, you should know that when people have lived for 43 years, pretty much one way as a blind person, they get good at it. And they understand what it's like to be blind, and they have a community of blind people. And it's very scary to actually transform yourself from somebody who would be blind into somebody who would be sighted. And you should know about Mike that he's a very special person. He's really quite a risk taker. And in fact, you're seeing pictures of Mike here well before he had his surgery. At the time, he was about 30, skiing downhill. Mike actually holds the world's record for downhill speed skiing of a blind person, which is 60 miles an hour. Exactly. And you can see him at the right as a young man shaking Ronald Reagan's hand because he won the gold medal in the Olympics. And if you wonder how, and the Paralympics, and if you wonder how somebody does that, they do that by skiing really fast and having the world's gold medal skier skiing in front of them and saying, jump, turn right, so forth. Okay, so this is serious stuff. But Mike's a risk taker. And he went ahead and had the surgery to have the limbic stem cell replacement and the cornea. And you're seeing a picture of him here at the moment when the doctor first removed the cover from the eye where it had been operated. And the head that you're seeing at the back of the right, he's reaching out to touch, is his wife's face. He had been married, had kids, had coached their soccer league, had done all kinds. He started a company, and here's the moment at which Mike first opened his eyes and could see his wife's face for the first time. And she was very, very moved at this moment. And actually, there's a video of this, and you can see she's quite frightened. What's he going to think? How's this going to go? And so forth. And I can tell you it went fine. It went fine. Okay, now, what I can also tell you about Mike doesn't see in the way you and I might imagine seeing. For example, here's a simple thing that I think most of you would relate to. I'm looking over here at this table and these computers, and from this point of view, they have a certain shape and size and so forth. As I walk around these computers and see them from a different point of view, they have a different orientation and shape and so forth. For you or for me, it's not a challenge to walk around these cubes or the audience or see somebody from a different point of view and recognize that they're really the same person. But Mike isn't capable of that. He will study something from a particular point of view and recognize it because he remembers it, because he's seen it in that way in the past. But it won't be automatic for him to just walk around to the other side. It'll have a different shape and angle, and he'll just obviously know that it's the same. It's really something that he has learned. And when I would sit and talk to Mike, say, well, how's that vision thing going? Are you seeing better? He'd say, well, yeah, I'm getting smarter at it. I'm reasoning more quickly about it. But as you know, for your own vision, it's not something that you reason about. It's something that happens pretty much automatically and with a kind of fluidity that Mike has never achieved. So for the next few minutes, I want to give you a sense of why it is Mike might not have achieved that fluidity, even though his peripheral vision has been restored. And as you know, the brain is where the interpretations of faces, objects, colors, and so forth take place. And this is a picture of the brain. The brain is a remarkably beautiful and complex structure involving, the cortex has maybe 50 billion neurons that are connected each about to 1,000 others, each one connected to 1,000 others and so forth. And it's really massively interconnected and quite a complex structure. And over the last couple of years, we can get reasonable measurements of human activity that were hidden from us. We can do this using magnetic resonance imagers, and we'll be able to actually measure the activity of the human brain in experiments called functional magnetic resonance imaging, as are illustrated here. In this particular case, you can see the brain is staring at the red spot. The eyes would be in the front, staring at the red spot. And you can see these expanding rings of activity of the stimuli cause a pattern of activity to move forward from the back of the brain to the front of the brain in a very regular pattern, which we call a visual field map. And we develop methods to measure the visually responsive parts of cortex and how the world is mapped onto the brain. And now it's quite a regular experiment. You can take, any of you can hop into the scanner, and half an hour from now we would have a map of your cortex. And we did that for Mike. And the first part you can see is we've zoomed in here to the very back of the brain. And on the right is showing you what the pattern of activity would be in a control brain, in most of you. And the very red means that that part of the brain is stimulated by the center of your visual field. And as you go to green and blue, it's the periphery. And if you just compare the pattern between a typical control and Mike, you can see that Mike is missing a lot of the responses in the very center of the visual field. And if you think of the things that you do with the center of your visual field, there are things like reading, which is very slow for Mike, recognizing fine patterns, and you have, in fact, a great specialization in your brain in the center. It's called the fovea, and Mike's is quite disorganized there. And so during those years, from 3 to 46, we believe that that part of his brain didn't develop in the natural way because it was deprived of the kinds of stimuli that would have helped it to develop in the normal way. The other thing that we know about the brain, and that is that the cortex is absolutely essential for, is interpreting features such as depth, facial expression, color. This is just to illustrate how massive these computations are, how significant they are. I hope you can see the white tile underneath the table and the black tile under the light there. In fact, the number of photons headed to your eye from those two tiles is exactly the same. Physically, that is to say, they're exactly the same. Let me just show you that by masking them up. And you can see that they're exactly the same. But they don't look the same to you because your brain is correctly interpreting them as, well, gee, one's in shadow and it's sending, say, 1,000 photons per second to my eye. The other's in direct light and sending the same number of photons to your eye. Well, the one that's in direct light must not be very reflective. It must be kind of a dark surface. And so even though they send the same to your eye, your brain interprets it. And if your brain has not developed to interpret these signals properly, you won't be able to see things well. There are specializations in your brain for color, for reading, for recognizing faces, and so forth. And these are illustrated here. And we, again, in one of these functional magnetic resonance imaging experiments, we could ask Mike to examine faces versus other things. And if in a typical control, the red parts of the brain respond when somebody's looking at a face, and the blue parts that you're seeing here respond when they're looking at some other object that's essentially matched for it. And you can see that they're nicely active and separated in space on the brain. When Mike did the same experiment, Mike would look at a face or he would look at an object. There was no distinction in the activity. His brain was not, the circuits had not developed so that he was capable of interpreting these. So a problem that we have to solve to help people like Mike is to find ways to cause those parts of cortex to develop properly when they're children or have them relearn as adults, to unlock the kind of rigidity that happens into the adult brain and help people like Mike. Now, the last slide and the last point I want to make about these people refers to the third part of how we'd like to help folks like Mike. Remember, I've already told you about the surgeries and the peripheral vision and now and the cortex. And now I want to tell you that one of the biggest things, and you can get a sense of this when you read Mike's book called Crashing Through, of this process, is the emotional support and the situation that you confront with your family and with your friends and your own identity and who you are. This fellow notes that I should be very ashamed were I to fall and people have to help me and realize that I could see only very little. When I go around as a blind person with my stick, he's sure of himself among people. But I feel I'm an object of respect and admiration, and I wouldn't want to lose that. And I think understanding people's psychology during these cases and helping them along is another very important part of what we need to do in treating these entire patterns. And this is something that we really hope to work on as an integrated unit here at Stanford and to have a real initiative addressing human health in all of its different forms. Thank you very much for your attention.